This is a multiple-choice question, testing your understanding of scikit-learn's model_selection module. Specifically k-fold and stratified k-fold for cross-validation. Let's see how well you grasp the concepts. This sets the stage for the quiz. We're working with scikit-learn, a popular machine learning library in Python, and focusing on the model_selection module, which helps in evaluating model performance using various techniques. Here, cross-validation with 5 folds is used to assess the model's robustness and prevent overfitting. This is a good starting point, before diving into the details of k-fold and stratified k-fold. This statement describes a property of k-fold. K-fold is a basic cross-validation technique. The statement claims it guarantees a stratified split. Let's analyze whether this claim is accurate. This statement concerns stratified k-fold. It asserts that stratified k-fold maintains a similar class distribution across folds. This is a key difference between k-fold and stratified k-fold, so pay close attention. Here, the effects of shuffle equals true and random state are being tested for k-fold. Shuffle equals true randomizes the data before splitting, while random state ensures reproducibility. Reproducibility is crucial in scientific studies to ensure the results can be replicated. This statement investigates the same properties. Shuffle equals true and random state but now for stratified k-fold. It's interesting to see if the outcome will be similar to statement C. This section introduces an illustrative dataset. While the actual dataset size and class distribution aren't explicitly given, it is mentioned to be illustrative and used for better understanding. This clarifies that the illustrative dataset contains 100 samples which, for simplicity, are assumed to belong to 2 classes, Class A and Class B. This is a great way to simplify the explanation. This is our starting point. A dataset containing 100 samples. This number is important because it influences how cross-validation will work. Remember, we'll be splitting these samples into folds. This is one method for cross-validation. Think of it like dealing cards. It simply divides the data into a certain number of groups, folds, without considering whether the different types of data, classes, are evenly distributed across those groups. It's a basic, straightforward approach. Unlike simple k-fold, stratified k-fold is a smarter way to divide data. Imagine you're sorting candies into bags, but you want each bag to have a similar mix of colors. That's what stratified k-fold does. It ensures each fold reflects the overall distribution of classes in the dataset. It's especially handy when some classes are rare. Okay, let's look at statement A. It says KFOLD guarantees a stratified split. Now, KFOLD is a simple way to divide your data into groups for cross-validation. It doesn't pay special attention to how the data is distributed among different categories. So, A is false. Statement C talks about using KFOLD with and a randomstate. The part mixes up the data before splitting it. The randomstate ensures the shuffling is always the same if you use the same number. This means you'll get the same folds every time you run it. Therefore, C is true. Let's move on to statement D. It's very similar to C, but uses stratified instead of KFOLD. Even though stratified makes sure each group has a similar mix of data categories, and randomstate still work the same way to make the results reproducible. It uses a random number generator to make sure the data categories are mixed up consistently when making the groups, leading to consistent results across runs. So, D is also true. This is a multiple-choice question testing understanding of scikit-learn's model_selection module, specifically focusing on the differences between k-fold and stratified k-fold for cross-validation. Let's explore each option. It involves analyzing the characteristics of each method and how they handle data splitting. Are you ready to dive in? The problem sets the stage by introducing the context we're working with. Scikit-learn's model_selection module and a dataset of 100 samples. The goal is to evaluate a machine learning model using 5-fold cross-validation. This sets the context for understanding why we need to consider k-fold and stratified k-fold. This statement explores the effect of the parameters "shuffle equals true" and "random underscore state" within k-fold. "Shuffle equals true" randomizes the data before splitting, and "random underscore state" sets a seed for this randomization, ensuring reproducibility. With the same seed, the data will be shuffled identically each time. Therefore, you will get the same folds. Think of it like a recipe. If you always use the same ingredients and the same steps, set seed, you will always obtain the same result. This is similar to the previous statement, C, but now focuses on stratified k-fold. The same principle of reproducibility using "shuffle equals true" and "random underscore state" applies here as well. Even though it's a stratified split, maintaining class proportions, the randomization is still controlled by the "random underscore state", ensuring consistent results across runs. These parameters are crucial for controlling the randomness and ensuring reproducibility in both k-fold and stratified k-fold. "Shuffle equals true" means the data is shuffled before splitting, preventing bias from the order of data points. "Random underscore state" sets a seed for the random number generator, ensuring the shuffling and resulting folds are consistent across different runs. This is akin to setting a specific starting point for a random process. Always using the same seed generates the same random sequence. K-fold is a simple method that divides the data into k-groups, folds. It doesn't ensure the proportion of classes is similar in each fold. The division happens randomly, and there might be class imbalances in the folds. Stratified k-fold improves on k-fold by ensuring a similar distribution of classes in each fold. This is particularly important when dealing with imbalanced datasets, where some classes might have significantly fewer samples than others. It aims to make the folds representative of the whole dataset in terms of class proportions.